Indeed. Maybe I was the responsible of the technical issue because when I went out from the room, the problem was solved. So, okay, let's go. And good morning, ladies and gentlemen. Good morning. Welcome back here for the day of this of the course. Today we are talking in India. We will start the mornings talking about, as you can see, simulation and in-shot peen. Okay, that is the what after having introduced the subject by means of recalling some papers that were published and that determining the evolution of the simulation of shot peening in the then I will move to the main aspect that must be considered when the simulation, in particular of finite element simulation of shot peening is done. That is to say, the material properties. Of course, indeed, shot peening is a complex physical process. Or indeed, what does it mean? That the phenomenon that is at the base of shot peening is not simple. That is to say, we have an impact of a ball against a target material, so we have no conformal that contact condition. It means that we have one non-linearity coming from the contact condition itself. And then we have another nonlinearity that indeed is due to the material behavior. Indeed, if you want to have as a result of shot, if you want to residual stresses, it means that we must induce residual in plastic deformation. And this means that the materials properties must be considered not only in terms of elastic modulus of Poisson ratio, but also for the complete constitutive equation, the relation between the sigma, the stress, and the epsilon, the strain. Okay. And then we have also to represent what? To represent the velocity and the high strain rate, at least when the shot of the impact happens at impact velocities that are inducing. Okay, and finally, we should not forget that if you want to relate the result of a finite element model with the result that we want to relate with the parameter we are using in the industrial environment for characterizing shot peening, must relate this result to coverage and to the Almen intensity. Okay, and this is also another complication, let's say. Okay. Then fine, this is most of the presentation will be about this subject, and then we will develop also some other development, some other aspects that were developed. Indeed, maybe I have already said yesterday that the simulation of shot peening was initially aimed especially or only to determine the residual stress. Indeed, we know now that shot peening is not just residual stress. We can exploit the microstructural modification, the surface work hardening, and also we can also analyze the roughness and the topography of the surface. And this is, and we have already told something about this aspect, but these are also important aspects that could be considered by means of simulation, and then and that with simulation, and that can reduce the experimental effort needed for developing a shot peening process. Okay. Okay, indeed, this is, we have already summarized what the introduction, let's say, is indeed just to introduce what that shot peening was initially considered more as a, let's say, an art, a black box where you put the shot, you put the Almen intensity, and finally, from the black box come residual stresses and the other aspect. But this is not true anymore. Okay, we can consider shot peening more as a result of a scientific study, scientific analysis, and this And this need, indeed, if we want to get this aim, we need to simulate, indeed, not only experiment are necessary, of course, but simulation can help us in reaching this result. But we should consider the different aspect that they have already mentioned, that is the nonlinearity due to the contact condition, plastic deformation, and high strain rate. And here I go back to the this delay. Anyway, I go back to maybe what can be considered as the first tentative attempt to simulate for shot peening, or better to develop what? To develop a model, a theoretical model that was able to relate the residual stresses, in this case, to the shot velocity and some other parameter. The author itself called it a rudimentary analysis of improving fatigue life of metathesis. He said that the model is rudimentary for the author itself. Why? Because with respect of shot peen, the real treatment, this is a very simplified model. That is, we are considering just one indentation, and also the relation is going to take, and the comparison with the experimental result is approximate. Anyway, by means of this, let's say, element simplified model, he was able to understand that the trend of the residual stresses, the fact that he was able to predict, to assess the maximum stress under the surface, and a realistic trend of the residual stresses under the surface. That is the typical one, let's say. So this is 35 years ago, and from that time, indeed, this was not considering finite element, but it was an analytical, simplified model. And from that time, many other models have been developed, mainly based on finite element. Okay, and this what you see here is the paper I mentioned that was published by me. Okay, and was indeed it has many innovative points, let's say, not only because indeed it was simplified, also this one was simplified. The software, the hardware at the time were not as evolved, as powerful as they are now. But anyway, in this case, we are able to represent the impact of more shots. And finally, the aim was to relate the residual stresses that we can obtain in a general part to what? To the Almen intensity that must be applied by means of simulation. And this, in this paper, many of the aspects that then were also used and developed in later years were represented. That is, the analysis was dynamic by using an explicit code. So it was 3D, three-dimensional, not axisymmetric, not simplified. Okay, and the code we used was Abacus, and this is the one that I use, and the group is using still today. We are considering more than one impact. Indeed, I don't want to go in the details of this model, but anyway, we have considered a zone around the point of interest with different combination. Okay, in such a way that shot peening was represented in a more realistic way, let's say. We use a kinematic hardening rule in terms of constitutive equation of the material. Okay, and at the time there was not such an equation implemented in the code, and so we developed a dedicated subroutine for the material. The hourglass control was also introduced. What is the hourglass control? It's typical for finite element. Indeed, the finite element can have some deformation mode, fictitious, let's say, deformation mode that are associated to zero energy. And so they are not real, but they can influence finally the result. And the hourglass control was also implemented. And the elastic wave rebound was also considered by introducing some infinite element at the border of the model in such a way that the elastic waves coming from the consecutive impact of the shot were not going to rebound and so were not going to influence the result themselves. And finally, the result was indeed, in terms of residual stress, it was satisfactory. And also, you can see here two of the scale with two different kind of shot. The relation with the shot velocity and the element intensity was also calculated and aligned with the experiment. This is another paper we published in 2010, and indeed this was published by colleagues working in Korean colleagues, and in this case, indeed, what the main point, the good point is this, in my opinion, that they are considering, they are relating somehow the simulation to the experiment that can be done for measuring the residual stresses. In this case, they are using the XR diffractometer. The XR diffractometer is measuring the residual stresses not in one single spatial point, but in an area around the point. That is to say, the X-ray spot have a finite area that is circular generally, and they have developed developed the model in such a way to correctly represent this area, and also the analysis of the result have been done by considering not single point, not single finite element, but also the complete area to have more consistent result. And the result they obtained were all satisfactory. Okay, and then indeed, and let's see. Oh, the screen is much faster than the laptop. Okay, and these are, and then could keep on talking about later newer the trend is the use finite element and to converge the experimental result with the simulation design, making the simulation as much as possible realistic. Later, we want. Can you? The microphone is that. But let's try. That if we want, say, of what of the dynamic, we can use not only. Yes. I imagine. Okay. Let's see. Thank you. Thank you. Okay, and then we another method for simulating the process itself. Not aim at the development of the calculation, determining residual stresses, microstructure change, but aim at simulating the process itself and the way the flow of the shot that we will see later. And this is how we can correlate also this discrete element method to finite element method. But let's go and let's talk about the main parameter that we should consider for correctly simulating shot peening. And the first are the material properties. Okay, as I have already said and underlined that shot peening is inducing plastic deformation, we know that, and so the material properties must be considered in the correct way. That is to say, we cannot simply put and the Poisson ratio, but we should correctly introduce in the code or distributive law in the elastoplastic region. So the considered equation, what is supposed to address the elastoplastic behavior of the material under static condition, that is during the first cycle. Then, since we have a repetition of the impact, we have a repetitive impact on the same point of small shots, we need also to have a description of the cyclic elastoplastic behavior. How the elastoplastic behavior of the material is changing when we have more than one cycle of deformation, one of the, in this case, more than one cycle for contact with the shot. The effect of the strain rate, at least in the cases that where the strain rate cannot be neglected, both because the material is not sensitive to the strain rate, and also in the cases that the strain rate is not important because the treatment conditions are too soft, let's say, to have an effective strain rate influence. And then another aspect is that when we are performing shot peening on material that have already been surface hardened by means of chemical treatment or thermal treatment, indeed, the properties are not constant through the depth. If we are going far from the surface, the properties of the material will change from the surface to the core. And also this aspect, if we want to have a more accurate solution, should be considered. Okay, let's talk about the first of all of the elastoplastic behavior. Okay, how can we consider the elastoplastic behavior? By defining the correct constitutive equation. And this is a function of the material. Each material with respect of the composition, with respect of the microstructure, can have a different elastoplastic behavior. And finally, there are different criteria that describe the sigma epsilon behavior of the material in this field. Okay, and also, since we are in condition where cyclic elastoplastic behavior is happening, okay, we an hardening rule that defines how the elastoplastic behavior of material is changing with the number of cycles. That is to say, an hardening rule. And the most widely used hardening rule are the so-called isotropic or kinematic hardening rule. What is that here are represented? What can we see here? Here we can see a sigma epsilon curve with deviation from linearity here, so this is the yield stress, and then we simulate here the unloading phase after having reached and exceeded the yield stress. In the curve on the right, we have the representation in the principal stress space, or in this case, plane. So we are dealing with a biaxial straight. The third principal stress is null. Here we have in the abscissa and the ordinate, we have two principal stresses. And here is the ellipse that defines the yielding condition according to the von Mises criterion. Okay? And according to the isotropic hardening rule, if the smallest one is the plasticity ellipse for the virgin material, so for uniaxial load, if you are exceeding the yield stress, the curve will increase, maintaining the same center. So it's expanding this way. What does it mean? That we will, if we unload the part and then we reload, the new yield stress won't be anymore the initial one, but will be the highest stress point that has been reached in the previous cycle. This is the isotropic hardening rule. The kinematic hardening rule is the other one that is here represented. Here we have, again, a material that with a deviation from linearity, so with elastoplastic behavior. We are exceeding the yield stress here, and in this case, the hardening ellipse remains with the same dimension, but is moving with the trajectory of the load. So in this case, if we have an uniaxial stress, if we are reaching the yield stress here, and then we exceed and we proceed with the test, the ellipse, the plastic ellipse will remain with the same axis, with the same dimension, but will move according to the path. In this, so if the load is uniaxial, will be in the vertical direction or the horizontal direction. Okay, which is the more appropriate one? Indeed, the isotropic rule generally is not correctly describing the behavior for most of the material of interest. Kinematic rules is better. This is what I used in the paper I commented a few minutes ago. But it's true that the best option is to have a rule that considers both aspects, because both the aspects are present in the surface, in the mechanical behavior of material. And one of the rules that is mainly used and is most implemented in the finite element call is the so-called Chabosh-Lemaitre hardening rule, with different grade of complexity, let's say. It is a combined hardening, isotropic and kinematic hardening rule, okay? And by means of some parameter, we are able to introduce these parameters in the finite element analysis and to correctly describe what's happening to the material and to correctly follow, to correctly follow the behavior of the material under repeated impact condition or impact point. Okay? Is it clear? Any question? Sorry. Yes, yes. Indeed, yes. Indeed. The Chabosh rules have many, has been, is used with many different formulas. The simplest one are present in Abacus. If we want to use more refined one with more parameters, we need to perform some experimental tests and then also to develop a routine. Okay. But for many material, the one that is implemented in the code is enough.
Elastic waves rebounding, that
Sorry?
that slide number 5, sir. That elastic waves rebounding,
Yeah.
no damping. How is it considered, like
Indeed, the elastic wave rebounding is an effect that if okay, if we have this elastic wave goes, reach the boundary, and then rebound back. And then, what does it mean? But this elastic wave will continue to go up and down. Okay. If we are using or some damping option, that is why we introduce in the material probably also a damping option, but we should, or what is to define, to complete model with the so-called infinite element. That is to say that of the finite element, we have is the behavior. And in this way, waves are free to to go without any rebounding effect.
That is material damp for the material damping.
Yeah.
But is it uses the like Kelvin model or Maxwell models like the KB model for damping, material damping?
Is another option. But and indeed, if damping, we can introduce some value just to dampen the waves, or if we know we should or perform some damping test to determine the structural damping of the material, or we should rely on by reference values.
Thank you.
You're welcome.
Thank you. Sir.
Okay, now let's go and see how we can detect. So the last behavior is done. Okay, let's see how we can consider the effect of the strain rate. And also in this case, there is not a unique way. But it's true that many materials can be described as regards the strain rate effect with the so-called Johnson-Cook equation. Okay, that is the one that you see here. Okay, we have 5 parameters, and we see that we can recognize the difference contribution. The first is the one, the static one, let's say, is an elastoplastic consider the equation that where the variable is the plastic strain, epsilon p. Okay, that is and then the second one is the term that is a function of the strain rate. Okay, so we have to know this is the elastoplastic strain rate, epsilon dot p, over a reference strain rate with this logarithm in logarithmic form. And then we have the other term that is related to temperature. So if we have a temperature effect, an effect of temperature, also this can be considered in the Johnson-Cook equation. Okay. Indeed, many times if shot peening is performed with soft parameter, let's say, indeed the temperature is not changing, so we can skip this, neglect this term, and sometimes also the strain rate is not changing the result, so in a relevant way. So also this one. In other cases, we must consider also this term. And if shot peening is very, very severe and induce some variation, okay, we should consider also the temperature in this case. Okay, not all the material are, the behavior of the material is always well described by the Johnson-Cook equation, but this can be used for many of them. Otherwise, if the strain rate effect is not important, let's say, we can count on the Chabot elastoplastic considered equation that I described in the slide before. Okay. Now let's go to the gradient of the material. When this is important, indeed, this could be important in many cases. From a practical point of view, this is important, especially for carburized steel. Why? Because carburized steel are widely used for gears, and shot peening of gear is one of the main applications of shot peening. Okay, in the power transmission industry, many times, most of the time, let's say, when the power to be transmitted is huge, let's say, we need to shot peen the gears. Okay, and so in this case, we start from shot peening is the last treatment, the final treatment, and the gears have been previously carburized or can also be carbonitrided. Anyway, they are surface hardened by thermal or thermochemical treatment. And so the properties are not uniform from the surface to the core. we have already seen here that the hardness is changing from a maximum to so, and then going back, and finally we have an asymptotic value that is the core. Okay, and how can we do that? Indeed, we had this problem in a cooperation we have with Rolls-Royce Deutschland, Rolls-Royce Germany, and and finally we used an equation that is this one, where the yield stress of the material is found to be related to the Vickers hardness by means of this equation. That is an empirical equation. Okay. And we also tried an inverse analysis approach, that is to say, by means of simulation and by means of experiment, to tune, let's say, the finite element model parameter in such a way to have the same indentation and the same result of the experimental measurement for hardness. Indeed, finally, the results were not so different, and by applying this formula that is found in this paper published some years ago by the University of Brescia, and we were able to correctly define the gradient of the mechanical characteristic of the materials. And the same can be done indeed with the inverse analysis. In this case, the inverse analysis means that that we have to develop more analysis, experimental numerical, to tune the finite element model. But for sure, an inverse analysis approach is much more general. Okay, if we approach the problem this way, we are not limited to carburized steels. Okay, while the formula given by Donzella can be used just for this kind of material. Okay, anyway, just to underline that if we have a previously surface hardened material and then shot peen, we need to consider, if we want to have more accurate result, we need to consider that the properties of the material are changing from the surface to the core. And we need some tool, let's say, to address this problem. Okay. Okay, now let's see the coverage. How can we consider the coverage? Indeed, we know now that real shot peening is formed, let's say, by the impact of 1,000 shots. Okay, even in a limited area, we have a shot flow that we said is around, could be even 80 kilo in a minute. We can imagine that the number of shots is quite large. And we cannot imagine to perform a finite element analysis by considering 1,000 impact, because it would be not sustainable from a time point of view. How much time do we need for this kind of non-linear analysis for the material and so on? It's not possible. So we need to develop some model that is able to consider the correct coverage, but at the same time is able to reduce the number of impacts that we need to reach this result. So the key points are these. We must define what is called a representative volume, or a representative volume unit, let's say. That is to say, something that is limited from a dimensional point of view, but is large enough to represent the complete material, in such a way that the result can be applied, can be extended not just to the representative unit, but to the large part. We must also consider that the nature of shot peening is randomic. We have not any preferential combination of the impact. They are quite random. And then finally, we need a relation that makes possible to relate the simulation result, the finite element result, to the real coverage value. Okay. And this is, indeed, this is what we have for representing the coverage. Indeed, the coverage, we know, we have 100% coverage when all the complete surface has been heated by at least one by the shot. When the complete when if we look at the complete surface, we cannot notice any unpinned portion of material. And we developed this basic unit, let's say. Here, indeed, here is when the impact are confined in the central part of the model. You see here, and we impose the analysis in such a way that the impact, the position of the impact of the shot on the surface was random. So a pseudo-random sequence of impact. Avoiding what? Avoiding that the pseudo-randomic sequence was not respecting the physical process. Is to say, two consecutive shots cannot affect the same point because this will be the impact will be prevented by the presence of the previous ball. Okay, but anyway, randomic, and you see here the sequence, the different balls that were represented. Okay, and indeed, I did say that if we are considering now it's working, okay? The shot peening means that the shot, we say that the shot must be quite harder than the treated material. Indeed, considering to simplify the model and reduce the computation time, we can consider the shot as rigid body. Okay? In this way, we can simplify the idea. In this case, was not the case. And here also, also one half of the shot was represented to reduce the number of degree of freedom, the dimension of the model, but the inertial properties of the complete shot were respected. Okay. And so here you can see this final element you see here are the infinite element I talked about before that prevents the rebound of the elastic wave, you see. And here you see indeed the evolution of the impacted surface. The white area is the area that has been impacted. So in this picture, the coverage is not 100%, but is something less. There are some blue area that has not been impacted. This is the situation of the impact indentation at the end of the simulation. And here we have the evolution of the impacted area with the number of shots, let's say. Okay, and to relate the evolution of the coverage, real coverage, with the result of the simulation, we use the so-called Avrami equation. That is an exponential asymptotic equation that we have commented already when, that is this one we have commented when we talk about the coverage. Okay, and in this way we are able to obtain what? The number of impact we need to consider the simulation in terms of coverage, to consider consider 100% coverage. Once and indeed we repeated the test many times, more time, in such a way to be sure that the number was a constant number, was not changing with the combination, with the randomic combination, okay? And in the end, it was found that we are able to reach full coverage, 100%, with 67 impact. You see? Okay. And you see here that the reference area, the circular one, is much larger than the area of the single indentation. Otherwise, it does not make any sense. And so once we know how many impact we need for 100% coverage, we can double the number of impact, okay, to obtain 200%. We can multiplied by 3 the impact needed for 100% coverage to have 300%, and so on, of course. Okay. Okay. And now an alternative way to deal with coverage and simulation, no more related to finite element, but to another method that was that been introduced more recently in practical application, and the so-called DEM, the discrete element method. That is a method, is a family of numerical method that is aimed at capturing and analyzing the motion of a large number of small particles. Okay, it is used not only for shot peening, this is just one application. I have used for some industrial cooperation the DEM for simulating the flow of the coffee beans in the grinding machine. Something like this, okay, to optimize the geometry of the blades in such a way that the machining of the coffee beans is more effective. Let's say just to introduce the method. It's close to molecular dynamics, but the method is generally distinguished by its inclusion of rotational degree of freedom. Okay, so we are able to include the rotational degree of freedom as well as the stateful content and often complicated geometry. Okay. This is the DEM is not considering plastic deformation. Okay, so you are not the Chabosh, not any plastic deformation, but it's good to assess the dynamic of the process in this case. And it became more and more popular. Why? Because today we have an increased computing power. And it's possible to simulate in a sustainable time even a number of a huge number of phenomena, let's say, of impact in this case. Okay, and here is a DEM model that was developed by colleague in Martin Levesque, he is at the Polytechnique in Montreal in Canada, and he developed this method where he used DEM for assessing the dynamic of the process, for assessing how the shots are impacting the target material, and then the result, as you can see in this scheme, are used as an input of the finite element model that is similar to the one that I have described in the slide before. Okay, so in the DEM model, he input the shot peening parameter, build a model for shot and target material by considering these rigid faces, rigid body, simulate the shot's flow, the shot stream, and then record what is the final result, the velocity at the impact and the location of the impact. Okay, and then these results are the input of the finite element model where we can analyze the residual stresses, the surface work hardening, and so on. Okay, is it clear? So the DEM is not alternative to finite element. It's something that is adding more information. Okay, we can simulate the process itself in a more realistic way with with many particles, let's say, without so much limitation. This is due to the computing power of the computer today. And in the end, but we have to deal with rigid bodies in this case at least. And so the result and then pass as an input for the finite element model to repeat the analysis that I have described in the slide before. This is another DEM, combined DEM, FEM approach. Yeah, this was developed at the University of Trento in Italy by colleague Matteo Benedetti. And here, indeed, this, just to show you, this is similar. The nominal shot peening parameter, then the setup of the EM model, that is the simulation of the flow through the nozzle. So we are talking about pneumatic shot peening, and then we have the everything. This goes from an input of the finite element, a simulation, and finally we have the residual stress. And this is done directly on a part, on this part that is, you see, severely notched. And this is also a good example of application in combination, the combination of DEM and FEM. Okay. Let's give some comment now, and then I stop and I ask you a question. Indeed, the evolution of simulation of shot peening, shot peening we said is a complex physical phenomenon. Okay, it's based on a complex physical phenomenon. That is the impact of shots on a material inducing plastic deformation with many impacts. So quite complex. And this means that from a numerical point of view, it's not simple to be simulated, It's not simple to simulate shot peening. And the evolution of the models of shot peening goes in parallel with the evolution of the hardware and the software, of course. Okay, there is, and today, indeed, the ability to use DEM is not new from the discrete element method is not new from a conceptual point of view, but this is used, has been used just from recent year. Why? Because before, at least in terms of practical application was not possible, a convenient application with the available computer. Today it is no more, today it is not true anymore, and so there is this other revolution that is occurring today. Indeed, there are different approaches that have been proposed to relate process parameters to the simulation, Kalman intensity and coverage, that are more and more complex, more and more accurate. But what I would like to underline is that the most important point remains the correct definition of the material parameters. If we have a very accurate model, very fine description of the process itself, but the material is not correctly simulated, also the result will be affected. And even if the model is conceptually quite accurate, the numerical result will not be very accurate, of course. And if we do not have a clear idea of the material properties, it's better to perform experimental tests before developing the model, in such a way that we can get with experiment the data needed to be introduced in the constitutive equation by Chaboch or someone else. Okay. And then another point, indeed, the evolution of finite element model has been based and been mainly oriented, let's say, to the determination of the residual stresses. And this is what I have also commented so far. Also the DEM, you see here the DEM model developed in Canada here. Finally, residual stresses are important. And then here, the residual stresses, but this is general. Most of the models are oriented just to capture the residual stresses. Indeed, this is not enough. Indeed, why? Because we know now that the residual stresses does not cover all the effects that shot peening is able to induce. We have other effects that should be considered: surface topography and roughness, and the microstructural modification, especially if you are going with high intensity or high coverage values. Okay? And this means that, indeed, but it's true that with finite element we can also consider this result and try at least to have an approximation and an evaluation and assessment of the real result. Okay, indeed, I have already commented with this slide. I don't want to spend any other time, but anyway, why to know the surface topography is important? Indeed, first, because we know for fatigue, the roughness is an important factor. So if the roughness induced by shot peening is large, we risk to lose, partially lose at least the beneficial effect of shot peening. But also because the surface finishing is also affecting other properties such as wear. We talk about bacterial adhesion, hydrophobicity, and corrosion, and so on. Okay. Here, indeed, we have, indeed, I would go fast. Sorry, I forgot to ask you a question. I said, after the moment I stopped, but I did not stop, so I stop now. And ask if you have any question for the previous slide. Shot peening?
No. How do we relate the surface roughness with the corrosion?
Indeed, with particular aspect of corrosion, type of corrosion, that is with interstitial corrosion or local corrosion. If we have very deep valleys, let's say, this could be preferential starting point of this local corrosion. This is, and so also knowing the roughness after shot peening in parts that are then loaded in an aggressive environment can help a better design of the treatment.
Okay. And sir, another question I have. For metals, generally, this is a layman question. What strain rate, are significant for metal, especially in Johnson's model? We have a elastoplastic part, then the strain rate part, temperature part. And what strain rates generally are important when we consider strain rate to be significant? What strain rate for metals actually?
For soft material, it's also quite low. In terms of numerical value, indeed, I prefer. We can discuss during the break. Okay.
Okay, sir. Thank you very much.
So I can be fine. Any other question?
Good morning, sir. Sir, in slide 19.
Yeah.
Sir, what do you mean by osseointegration?
Osseointegration is the ability of, imagine a prosthesis or anyway an external body, okay, it could be also a screw that is inserted into human body, and osseointegration is the ability of this external body to be integrated into the bone and then to permit the growth of the organic tissue of the bone itself without without any negative effect, let's say.
Thank you, sir.
Any other question? Everything is clear?
So many things are not clear, so I thought I'll just go through it again and then I'll ask you
Okay,
questions.
okay, thank you. So we can proceed now. Okay, indeed. I have already commented a study like this that we did about the cell adhesion and so on, so I will go. We have already discussed yesterday, and so the importance of knowing the importance of roughness topography. And then I have already discussed yesterday, we have discussed this model for calculating the roughness. Okay, just indeed this was a combined model that you consider Abacus and Python development, so finite element analysis, and then by means of a abstract code, we are able to distinguish between the numerical noise, the waveness, and finally to calculate the roughness that is then well aligned, let's say, with the experimental values. This is already done last year. And indeed, yesterday I said that in the model that we have developed, we started from a perfect surface, completely smooth. But indeed, in real cases, this is not always true. Not always the real surface can be approximated by a completely smooth surface. And this is in particular, this is true for, I also said, for additive manufacturing phases. Here you can see some example of free surfaces of part material obtained by laser SLM, that is today is called laser powder bed fusion or selective laser melting. And here we see the surface state. What does it mean? That the initial surface is quite far from a smooth surface. So if we are going to perform some calculation like this on additive manufacturer part, the result cannot be realistic if we do not consider the real initial state. And this is what we did with this model. Indeed, the model is the same, the concept is the same with the infinite model with an elementary cell here, and you see here the initial state. The surface is not smooth, but is rough. And the way the roughness introduced comes from the digitalization of the real surface by means of AF. Let's see, okay. The data defining the surface, so we can reconstruct digital surface by means of, also by using some filter to avoid numerical singularity. And then we can use the final surface we have obtained and elaborated this way as the input. So you see here introduced into the finite element. And starting from the deformed surface, the model has been then defined and introduced in the usual one with the, again, infinite element at the end of the model. Okay. Also, in a treatment was considered, so the surface were acquired, were digitalized, both before and after the surface, the treatment, the post-processing in terms of heat treatment. Okay, here we can see the different static behavior, sigma epsilon behavior of the material as built, blue line, and after the treatment. That is much more ductile. Here you see. Okay, and then what have we done? We have considered the two different surfaces, okay, before and after the treatment, and in the shot peening model, shot peening process model simulation of this case, we have considered both the constitutive equation of the build condition and after the treatment. And these are the mechanical properties we use. Indeed, the elastic modulus is not changing. The material is an aluminum alloy. The 207 to so is the final elongation and failure percent, so much more. Okay. Here we started from the Johnson-Cook model, but we know strain rate was not affecting the result. Okay, and so finally this was the final Johnson-Cook model effect. Okay, you see here that there is a very good overlapping between the experiment and then the Johnson-Cook prediction for the two cases. Okay, and again, the shot peening was simulated using a randomic sequence of impact of the shot, following the way we did what we have already developed in the previous model, not dedicated to additive manufacturing. Okay, and finally, in this case, the desired 100% coverage is obtained after 200 shots for this case. The material is for the in addition. Okay, just to underline that if we are say that strongly deviates from a perfectly smooth surface, we need to consider the initial state. Otherwise, the final result will be not respected, will not accurate. Okay. Here we are dealing now with the last aspect of shot peening simulation, that is grain refinement. Or grain refining due to shot peening or to other possible impact treatment. Here you see some of the we have developed. In this case, this is you are considered fatigue behavior notch specimen with nanocrystallized surface, and this other one is a paper that is dealing with wear. Okay, and also this, indeed, in the for grain refinement, we have already commented this slide, so no reason to spend so much time, just to see that this is not pin, conventionally pin and severely pin samples, and in this case, you can appreciate that the depth of the surface that is affected by grain refinement is increasing with the intensity and the severity of shot pinning. And also we can also see that shot pinning severe shot pinning is able to induce phase transformation to austenite, to martensite. Okay, we already said that the key factor in a simulation should be the ability to assess when the deformation reaches at least 6 to 8, let's say, and this is the condition that make possible the prediction of grain refinement. Okay, indeed, this is the model we have developed in terms of for grain refinement. This is quite similar to the previous one. Okay, and also the issue, the aspect that we have considered are the same. So material model, mesh convergence, coverage assessment, and the randomic nature of the process. And again, the model that is shown here is the same I have already talking about refinement. So this is just to remind that what can be done, that the approach should be something like this. In this case, something that relates, that he consider both finite element simulation, here where we induce spinning parameters and we start simulating dislocation density growth theory by Muga for assessing what? For assessing for having the population of the parameter dislocation was then element result. And the finite element result to give us the total plastic deformation. Mixing the plastic, the total plastic deformation result coming from the dislocation density, able to have an estimation of the finally of the crystallized size and then the grains. Here are some results obtained by a TEM. The TEM was MIT said yesterday this was done in collaboration with Professor Schutz. And then also the result in crystallized size are given also with comparison with the SEM and the TEM. Good agreement between the model developed and the okay. Late now. Simulating is not a new science. Model I said was that date back 1990, so 35 years ago. The evolution in the direction of finite elements. So finite element the most widely used tool for operation. Why? Because it's the method that allows assess the three shot peening, traces, work, and finally also. And indeed, future development are now not considered so the residual, and we also apply we also in combination with finite the representation of the process, even more and more realistic results. Reduce computer. Another way to go could to develop, okay, and that could be able to make happening at the smaller level of scale into dynamic or something later, the computer for it much more, but also the intrinsic time the experimental method that we are getting in this year, okay, can also help in achieving a deeper understanding of the process itself.